Dive right into this explainer. Today, we're decoding the invisible forces that govern literally everything around us, from a massive high-speed collision all the way out to the fabric of our universe. We are looking squarely at dynamics, and this isn't just about watching how things move, it's about figuring out exactly what causes them to move, to stop, or to completely change direction in the first place. And, understanding these forces isn't just some theoretical classroom exercise. It is absolutely a matter of life, death, and precision engineering. When researchers are out there designing cars with better safety features, they're using high-speed collisions to study the brutal, visceral reality of dynamics. We aren't just doing math on a chalkboard here, we are breaking down the fundamental rules that dictate our physical reality.
But before we can really understand how a vehicle crumples on impact, or say how planets orbit the sun, we've got to start with a pretty foundational question. What actually is a force? I mean, we use the word all the time, right? We force the door open, we force ourselves out of bed on a Monday. But in the strict realm of physics, what is it, fundamentally?
Well, here is our roadmap to figure that out. First, we'll look at the nature of force. Second, inertia and acceleration. Third, action and reaction. Fourth, the friction factor. And finally, universal gravitation.
All right, let's kick things off with Section 1, the nature of force, pushes, pulls, and physics.
So at its absolute core, a force is simply a push or a pull acting on an object. And we measure this in units called newtons, named after Sir Isaac Newton, naturally. But here's the catch. In the real world, an object rarely has just one single force acting on it at a time. Think about a stalled truck. You've got two people pushing it from behind, but you've also got the friction of the road aggressively pushing back. The net force is what we call the vector sum of all these different pushes and pulls happening at the exact same time. It's basically the mathematical bottom line. It dictates what the object is actually going to do. If all those forces perfectly cancel each other out, the net force is zero and nothing changes. But if they don't cancel out, well, things are about to move. Which brings us right into Section 2, Inertia and Acceleration, exploring Newton's first and second laws. Okay, so Newton's first law basically says that an object is perfectly happy to stay at rest or to keep moving in a perfectly straight line at a constant speed unless a non-zero net force comes along and interrupts it. It's easiest to think of inertia as just an object's absolute stubbornness. It wants to keep doing exactly what it's already doing. Like a hockey puck gliding on perfectly frictionless ice, it would theoretically just glide forever. Now, Newton's second law tells us what happens when we actually overcome that stubbornness, and that is acceleration. When a net force finally acts on an object, that object accelerates directly in the direction of the force. And this equation right here brilliantly captures his second law in its purest mathematical form. Net force equals mass times acceleration. F equals ma. It is literally one of the most famous equations in all of science. It tells us that the harder you push something, the faster it speeds up. Simple enough, right? But it also means that the heavier something is, the more mass it has, the more force you are going to need to achieve that exact same acceleration. It's why you can effortlessly toss a tennis ball across the yard, but trying to toss a bowling ball with that same amount of force, yeah, you're barely going to get it moving. Moving on to Section 3, Action and Reaction, or Newton's third law. This is such a great example. We're looking at Duff Gibson at the 2006 Winter Olympics, just absolutely charging headfirst down an icy track in the skeleton event. To reach speeds over 125 kilometers per hour and clinch a gold medal, he couldn't just passively lie there and slide. He had to explosively push backward against the ice. And the ice pushed him right back forward.
And that interaction perfectly captures Newton's third law. Forces always travel in pairs. Every single action has an equal and opposite reaction. If you push on a wall right now, that wall is pushing back on your hand with the exact same amount of force. When Duff Gibson pushed backward on the ice pushed forward on him with equal magnitude, and that's what propelled him to Olympic gold. It's kind of wild to think about, but you literally cannot touch something without it touching you back with the exact same intensity.
Let's jump into Section 4, the friction factor, and why we don't just slide around forever. So, friction is the great resistor of motion, and it comes in two very distinct flavors. First, you have static friction. This is that invisible force keeping a stationary object stubbornly stuck in place. Then you have kinetic friction, which is the continuous resistance you feel when an object is already sliding along. This whole face-off explains why it takes so much more effort to unstick a heavy, stationary box from the floor, because you're fighting static friction, than it does to keep it sliding once you finally get it moving against kinetic friction. See, the microscopic ridges of the box and the floor essentially lock together when they're resting. You have to break that initial lock before you can get to the slightly easier job of just sliding over those bumps. And finally, Section 5, Universal Gravitation.
We are scaling things all the way up to the cosmos.
Now, it's really easy to think of gravity as this uniquely earthbound phenomenon, right? It's the thing that pulls our dropped phone to the floor, it's what makes our legs feel heavy at the end of a long day. But wait, what if I told you that the exact same principles stopping that sliding box on your floor are also governing celestial bodies millions of light years away?
We intuitively know gravity as this massive downward force. It's what an ice climber is physically fighting with every single grueling step up a frozen mountain. To that climber, gravity feels localized. It's a relentless pull straight down. It's what gives them their weight. But Isaac Newton realized something so much bigger than that.
He figured out that gravity isn't just an Earth thing. It is a fundamental force pulling any two massive objects together across the entire universe. His law of universal gravitation states that absolutely everything with mass attracts absolutely everything else with mass. The more massive the objects are, the stronger the pull. However, the farther apart they get, that force drops off dramatically, which is what the math means when it says inversely proportional to the square of their distance. This is the invisible tether holding the moon in its orbit around the Earth and the Earth in its orbit around the sun.
And here's where the whole thing gets truly mind-blowing. Remember Newton's third law from a few minutes ago? Action and reaction pairs? Yeah, it applies to gravity too. Earth pulls you down with gravity, but did you know that you are pulling Earth up with the exact same amount of force? Seriously, if you weigh 700 newtons, Earth is pulling you down with 700 newtons of force. But you are also pulling the entire planet Earth up with 700 newtons of force. The only reason you don't see the Earth leaping up to meet your shoes is because Earth's mass is just astronomically huge compared to yours, so its acceleration is effectively zero. But I promise you, the pull is there.
Which brings us to our final takeaway. Because you have mass, you are currently exerting a gravitational pull on the very screen you're looking at right now. And yep, the screen is pulling on you too. Your coffee cup, the walls of the room you're in, the distant stars, you are physically connected to all of them through this invisible, fundamental web of gravitational force. You aren't just observing the dynamic laws of the universe, you are an active, pulling participant in the whole shebang. So I'll leave you with this thought. The next time you drop something, don't just complain about it falling to the ground. Ask yourself, how much did the ground fall up to meet it?